G'day, I'm Robert Ellis, the Old Master Coach. If you've seen my previous videos on calculus, you know how to differentiate a function. At least you know how to differentiate a polynomial. Today I want to go through sketching a curve, such as a cubic polynomial, using calculus. Now, in sketching a curve, as opposed to graphing a curve, we need, if it's a 3-powered polynomial called a cubic, we need just 4 points, and I'll demonstrate the 4 points that we need. We need a point where the derivative is 0 and the second derivative is less than 0. That gives us a maximum value of the curve. It doesn't get any higher than that in that vicinity. You'll notice over here it'll get higher. So we call that a relative maximum. So that's the first point. And we have, as an opposite to a relative maximum, we have a relative minimum, which is this point B. Over here, you'll notice that the derivative of the curve, the slope of the tangent, is 0, dy by dx is 0, and the second derivative, because it's concave up, is greater than 0, whereas concave down over here for a maximum, the second derivative is less than 0. Now, somewhere between being greater than 0 and less than 0, there has to be a point where it passes through 0. Now, if you have a look at this bendy ruler here that I have in front of me, if we have the maximum up here and the minimum down here, somewhere between there, there's no bending or no flexing. The prefix for no is often in, like invisible, not visible. Well, inflection means no flexing. So we have what we call a point of inflection between A and B, where the second derivative is equal to 0. Now, for a cubic polynomial, this point D here is exactly the midpoint of A and B. If you draw a straight line between them, then D should be on the midpoint of that straight line. Now, don't find D by finding the midpoint. What I recommend students do, they find the midpoint by solving this, and then check to see if this is the midpoint, and if it is, then you're pretty certain these 3 points have been worked out successfully. Particularly in an exam, that's important because it's quite easy to make a simple mistake, and that's a good, quick way of self-checking in the exam. It would be just a matter of going through and finding where the error was. Now, once you've found those 3 points, the last point that you need to find is the point where it cuts the y-axis, which I call C. Now, using those 4 points, you then sketch a nice smooth curve between the 4 points. Now, a lot of students just don't put the scale on their graph. You must show a consistent scale on the y-axis and a consistent scale on the x-axis. They needn't be the same scale. For instance, if this is 40 and that's minus 20, and this is minus 2 and that's 5, then you'll have scale along your x-axis perhaps at 2 centimetres equals 1 unit, and on your y-axis you might have a scale of 1 centimetre equals 5 units, or 1 centimetre equals 10 units. Or use the lines of your page and say each line of your page is 5 units, and that's preferably. My preference is always put the axis on the line of the page and use the lines of your page to mark your scale on the y-axis. A, it saves you time, and B, it's dead accurate. You don't have to get your ruler out and measure it, and you're not looking at lines between lines. So your x-axis on a line of the page, and the lines of your page, use them to mark your scale. Sketching polynomials is really easy, and I've set out a mask which you can download and copy into the mask to solve problems. Now, I'll now do one of the simple questions on the whiteboard and show you how easy the problem is.